Hi everyone, in this video we're going to be looking at how to determine the polarity of molecules. So step one is to determine the difference in electronegativity of each bond in the molecule, and then step two is to determine the molecular shape. And once we've done that, we can combine those two factors in order to work out if the whole molecule is polar or not. So we're going to use a few examples. And the first one that we're going to start with is water. So let's just draw a Lewis dot diagram of that structure. So you've got, in water, you have got two OH bonds. And the OH bond, from our previous studies in electronegativity, is indeed a polar bond where the oxygen is drawing the electrons to itself more so than the hydrogen. So it is classified as delta negative and the hydrogen is classified as delta positive. Okay, so there is what we call a dipole in that bond. So if we have a look at the molecule shape itself, and the other thing to note also is we're going to do a little bit of work in vector addition. So the arrow is always pointed to the direction of where the electrons are going to be attracted. So in this particular instance, we've got a net attraction of electrons in the direction of the oxygen molecule. And in our previous studies of a molecular shape, we know that water is a bent molecule. And so all we're going to do now is we're going to do a little bit of vector addition. And with vector addition, we've just got to note the point where the vector starts and then the point where the final vector finishes. So we've got the first force, which is this one here, attracted towards the oxygen, and then the second one is attracted towards the oxygen in that opposite direction. And so overall, we say the net force of attraction is going from the start of our first vector to the end of our last one. So it's going towards the oxygen. So yes, because both vectors are going in the same direction overall, the net force is of attraction of electrons towards the oxygen atom, and so water is indeed a polar molecule. Let's now have a look at carbon tetrachloride. So carbon tetrachloride is a tetrahedral shaped molecule, and it's got the carbon chlorine bond. So the carbon to chlorine bond is as well a polar molecule, but in this particular instance, the carbon is delta positive and the chlorine is delta negative. So the chlorine is the atom that is attracting the electrons towards itself. It is more electronegative. So it's always going to be the more electronegative atom that draws electrons towards itself. And the arrows then are going to be facing from the carbon out towards the chlorine atoms. And so you can already start to see that these are going in opposite directions. And so if we did a little bit of vector addition here, in this case, we would have, if I started here, just go the same color. If I started here, then we've got one arrow going up, across to the left, down, and then across to the right. Note here that the last vector is ending at the same point as the first vector starts. So in this instance, we say there would be no net force of attraction. And so that means that even though that this molecule has 4 polar bonds, it is actually non-polar, okay? Because you can start to appreciate that this chlorine is attracting electrons towards itself, and this chlorine atom is attracting electrons towards itself. So there's going to be an equal pull of electrons on either side of the carbon atom. Okay, moving right along, and we've got methane, another tetrahedral molecule. This one is a little bit more straightforward because the carbon to hydrogen bond there's low difference in electronegativity between the two atoms. So this is nonpolar. There is no area of slightly positive or slightly negative. So it's a nonpolar bond, and it's a nonpolar molecule. And then we're going to move on to carbon dioxide, which is the carbon atom with two double bonds and the oxygen atoms on either side. Now the carbon to oxygen bond is also polar. So the carbon is delta positive, and the oxygen is delta negative, being the more electronegative atom. And what we're going to see is the electrons being attracted to either either oxygen atom. And once again, if we add those vectors up, we would have one going in that direction and then the other one going in the opposite direction, and that's going to be no net force as well, which means that, again, while our molecule has two polar bonds of carbon to oxygen, it is overall a non-polar molecule. Okay, moving on to ammonia, which is our trigonal pyramidal shaped molecule with the nitrogen and the 3 hydrogen atoms attached. If we look at the bonds that make up this molecule, it is 3 of the NH bonds, and they are indeed polar. So the nitrogen is electronegative and the hydrogen is what we call electropositive. And so the force of attraction is up towards the nitrogen. And again, if we did that in the form of a vector, we have the start of the first vector to the end of the last one. There is an overall force of attraction towards the nitrogen, and we then classify this molecule as polar. So it all depends on the shape of the molecule as to whether a molecule that has polar bonds will end up being polar. Okay, if there are non-polar bonds in the molecule, then it's very clear that that molecule will be overall non-polar. But if it has polar bonds, we really need to take into consideration the molecular shape. And the last one we'll do is a little bit more challenging because it's got a variety of different bonds, and this one is ethanol, C2H5OH. So it's got a few different bonds here. It's got the CH bond, it's got the CO bond, and it's got the OH bond. And of those 3 bonds, CH is non-polar. The CO, as we've said above, is polar, and the OH, as we've said above, is polar. And so we're just going to focus primarily on the OH bond over here. But essentially, because we've got a net force of attraction towards the oxygen and even from this carbon, then this is going to be overall a polar molecule because there's no other force of attraction towards electrons in an opposite direction that would be cancelling it out. Okay, and this is a bit of an interesting molecule because it exhibits properties of both non-polar molecules, because it's got the CH bonds, which are all non-polar, and it exhibits properties of polar molecules, so we'll talk about what those properties are in more detail in later studies. But I hope that has helped you in determining the polarity of molecules.